works. But in reality, you have something like this, where the proxy is applying these voltage pulses. But then if you did have a view like a TCAD or a TCAD simulation of it, what's going on inside the EMCCD, this is how the charge is moving across from phase to phase. And it's really important, for example, to make sure that the overlaps of these pulses are in the correct position, that the amplitude does not rise too quickly. Things like that for an EMCCD can substantially impact your noise performance. So the cameras, those three components, were all assembled and tested in our lab, and we have requirements for each of the cameras that meant that they could do their job for either ExCAM or LoCAM respectively, and they're summarized in this table here. A lot of work went into generating this table, and in many cases we were meeting the requirement by a very large margin. We performed some very specific modifications. For example, for read noise, the cameras as delivered were meeting the requirement of 200, but they were about 200 electrons. But we performed hardware modifications to remove things like grounding loops, and we had software modifications as well in order to beat the noise down as much as we could for ExCAM and LoCAM. And I wish I could tell you that this is the end of my presentation and that this table was the best performance that we saw, and that I won the Nobel Prize for EMCCD optimization. Took my early retirement and flew off to Hawaii. However, you've probably guessed by now that that is not the end of the story, and something that I have learned when working with scientific instruments is that it's easily to be very quickly humbled, as I was when we plugged into the cameras on the instrument test bed, not on the instrument test bed, sorry, on the during integration and test, and we powered them on for the first time. And our first noise result was 750 electrons, which does not meet the requirement that we had at 200. So that sounds like a large number. It is a large number for a CCD read noise. However, to put that into context, the CCDs are incredibly sensitive and they're purely analog. If you convert that noise into a voltage, you're looking at just shy of a millivolt of electrical noise that's coupling onto the output. So amplitude is small, but the CCDs are very sensitive. So this was a problem that we needed to work on. And something that was incredibly useful for us was the functional test bed, which had the EDU camera and a representative setup very similar to what was on the flight bench. And we went there with equipment and we did different tests with different grounding configurations. And we found that there was a ground loop in the power cable that was supplying the voltages to the proximity electronics. What it was is that there's an external shield for the cable, and essentially when we disconnected that shield of the power cable, it removed the ground loop and reduced the noise substantially. I keep talking about noise, I should quantify it a bit more. The noise that we saw had a very repeatable pattern. It would repeat every 20 pixels, so about 500 kilohertz, and that corresponded quite closely to the frequency, the intrinsic frequency of the switching power supplies on CGI. So it made sense that this noise could be coming from another unit, but coupling to the camera through a ground loop. And once we found this, I have to say a big thanks to the project. We all worked together very quickly in the space of, I think, just over a month to manufacture and install new cables that had this shield isolated. We made some other modifications at the time to reduce susceptibility to EMI, EMC, and try and improve performance further. That included modified ground straps and a modification to one of our thermal connector cables to remove an unwanted connection to chassis ground that could have impacted the camera. So this was the first effect that we saw from plugging in to the instrument, which was this excess noise. The other effect we saw was something called overshoot. We termed it overshoot, undershoot, and I'll explain what that was. So looking at our signal chain again, if you look at the analog data that comes back out of the EMCCD, you have a waveform that looks something like on the bottom left. So that's 1 pixel's worth of signal. And what happens is that it's a purely analog signal that goes to the proxy, and the proxy samples it at 4 points and those dashed lines there, and uses that to reconstruct your image data. The higher the difference between the lines, the brighter the signal within the image. Now, there are settings on the camera to what waveform it's going to expect, because when it does that sampling, it needs an adequate estimation of where approximately the voltage is going to be. Since it's running at 10 megahertz and it's quite fast, the estimate needs to be quite close to reality. The problem was that changing the ground meant that it was no longer close enough for the camera to provide images that were useful for science. And we had something like what was on the top here, where signals, when they went from pre-scan, the dark, to signal, they would go brighter than they should before decaying down to a regular signal level, and vice versa when you went to dark. So this was not hardware modification. This was now software modification, where we changed the pulses that were going to the EMCCD in order to match what the proxy expected to what the proxy received. And then that gave us 140 electrons without this image artifact here, which for a room temperature measurement, room temperature is always slightly noisier than cold. This was in line with expectations. Now, there's one other thing, though, that this showed us that we needed to do, and this had to happen when we were cold, and that's retuning EM gain. Now, at the start, I showed you that HV pulse position and control is incredibly important. And with the HV pulse that's generated on these cameras, changing the ground changes the effective impedance at 10 megahertz, which can change a shift in the effective position of this HV pulse, which changes the EM gain response. And as we expected, when we performed measurements of the commanded gain, what we thought we had calibrated versus measured, they were lower than expectation, showing that basically the pulse was misaligned compared to where it needed to be. So what happens here in the camera is, just because you throw 40 volts in, that doesn't necessarily matter. What matters is what the charge sees when it's transferred, which is not necessarily the same amplitude. And when the charge is transferred is when this red line starts to decay here. So I wonder if I can play that again. But if the pulse is misaligned, because the red line is here, even though it's 40 volt amplitude, it could only see, for example, about 36 volts, so lower than expected. And if it's severely misaligned, the challenge really is that while that charge is moving, this HV pulse is still changing in amplitude, which means that you can effectively witness a change in EM gain versus signal level, which we see as nonlinearity. So this was a potential, performance concern, and we needed to realign the HV pulse in order to recover EM gain and linearity performance for both ExCAM and LoCAM. It's something that's simple enough to do, and I'm just going to very quickly provide you like the masterclass in how to tune each of these two cameras for EM gain. The first thing you need to do is stabilize the temperature. The circuit has got an inductor in it with a temperature coefficient, and it means that that pulse will move as a function of proxy interface temperature. So you need to be stable for this measurement, otherwise the pulse will continue to move. Then you have the coarse alignment, which is moving the black line by 3.125 nanoseconds, which sounds good for a resolution. However, it's still not quite good enough to perfectly align the pulse with the charge release point of R-phi1. So what you do then is, after the coarse alignment, you do the fine alignment. And this is the subtle bit. For the R-phi1 pulse, for the charge release point, because it's an RC curve, changing the amplitude of it also effectively changes the timing at which the charge is released. And so this provides us a means to do very, very fine alignment for HV tuning with over a 10 times timing resolution compared to just moving the HV pulse alone. So for coarse alignment, if you look at this plot here, coarse alignment approximately corresponds to the difference between the red and the blue curve, but then the fine alignment, which is changing these dashed lines in amplitude, corresponds to the points on a single curve. And so what we do is we pick the maximum, and then we have a voltage for this specific pulse, and then we get EM gain that is what we expect, and we recover the linearity performance as well. So we changed all of the settings to make the cameras work as we would then have expected. One of the changes we needed to do, however, was change a voltage called the substrate voltage, which impacts many things on the detector, but one thing it does impact is dark current. And so we've seen an increase in dark current compared to pre-delivery. And that's because there's now a greater fraction of the pixel contributing to surface dark than there was pre-delivery due to this change in operating voltage. This has, however, resulted in a reduction in the CIC. We're below now 1e to the -2, operating at gains of 7 to 8,000, which for an EMCCD camera is very impressive. So that was nice to see. So we've got the maps here showing over the 1K by 1K area, the dark and the clock-induced charge map. The linearity at unity gain, very good, basically error limited performance as you'd expect for an EMCCD. And then again equals times 200. We do see a few percent. However, this was better compared to the pre-delivery result. and the cameras worked as they're expected for both LOFUS and HOFUS. So we know that this sort of level is no longer a concern for us. So for read noise, we ended up with about 165 electrons. There's still some residual 500 kilohertz noise. However, we're below the requirement of 200 electrons. And the full well, we're just shy of 90 kilo electrons, which is close to the pre-delivery value. Some very basic analysis for read noise, because that pattern is fixed from image to image. You can use some quite basic techniques to do noise subtraction and give yourself 15 electron reduction. And this was very quick and very basic. I'm sure more advanced techniques can perhaps give you even better yields if you start to focus specifically on the spikes at each of the peaks of those sine waves. So this is the summary, giving the delivered performance values compared to the requirement. We are below the requirement for read noise. Things like full well, things like linearity performance is very good. We've seen the increase in dark current, but after talking to the team, we know that this is not a concern, and we do have still the capability to cool the EMCCDs further throughout the mission life if we do need to reduce the dark current due to radiation damage. So I think I'm out of time, so I'll end there. But of course, if you've got questions, you can ask or catch me a bit later on.
Any questions for Nathan? Not I have one.
Yeah,
quickly. Let's do with the lifetime of the camera and tests made in.
You mean the radiation damage effect? Yeah, there was a campaign performed by Patrick Morrissey and Leon Harding. It was actually before I joined JPL. They took devices very similar design to what you used for flight, and they tested them for radiation damage to the 5-year dose, and they performed, they performed consistent with the requirements that you're showing. We're showing here. So,
So they're shielding efforts and everything.
Yeah, exactly.
So to add to that, my understanding is the process of photon counting, where you accelerate the electron packets and create collisions and amplify the signal, is destructive in some way.
Oh yeah.
What's the lifetime associated with that process?
Yeah. So that was So that's signal aging. Yeah, people call that. And we did some testing, which I didn't talk about here, but during my time here at JPL. Specifically for LoCAM, because that's higher signals using moderate gains, 200 to 1500. And we found that basically, if you consider the total detector life at about 5 volts, which is what Teledyne estimate the point at which you can't use the device anymore after that, we are not expected to get anywhere close to that, even operating at 5 years. I think we were around just over 1 volt. And the way that aging proceeds is that it exponentially decays the more signal you pass through it. So if you were to spend 8 months on LoCAM doing something, the subsequent 8 months would then do like 50% of what the previous 8 months did, and vice versa. So we don't really have any concerns for signal-induced aging, which until we did this investigation was a bit of a concern, and there isn't much data on it.
So are there bright limits associated with that issue then?
Well, if you run the detector fully saturated at gains of a few thousand, then degradation can occur quite quickly, but that's not a science use case for these cameras typically. As long as you're running, in the way that you would need to actually measure the data that's coming out of the cameras, we saw that it was actually really hard to kill them. And in fact, during the investigation at the end, I tried to kill the device and couldn't in the time I had. So there are limits, but it's hard to hit them, I guess. Okay. Yeah, great, thanks.
So you had a nice table of the commanded EM gain versus measured retuning. What was that like after tuning, and kind of how stable do you think that mapping is once we launch?
So at the moment it's 1-to-1, but we kind of recalibrated it. So we fitted a curve to what you actually measured, and that is now what you receive when you command it. And there's a small error bar on that because it is a fit to data, but the error is quite low. And I'm sorry, you had another question.
Post-launch, is there a plan to kind of check that calibration?
Yeah, there's nominally plans. I don't know if I think Eric might be on the line, but I think nominally, I don't think it's set in stone. But every few months, I believe we have a plan to recalibrate the EM gain based on what we did in TVAC and based on the signals we expect ExCAM to see. I do not expect significant shift like between those 3-month periods. It's just that it is a good idea to remeasure occasionally. So it will.
They're going to do some measurements of contact once it's CGI is connected to the spacecraft, so the grounding configuration will change. So during the upload in the next 2 years, we'll repeat it a couple times.
Ja, det är one more time and over.